Evening, everybody. Hello.
Good evening, sir.
Hello.
Happy New Year,
Evening,
sir.
everybody. I said all have vanished because I was late. Sorry for that. I think we don't expect anybody else to join. Shall we start? Are you able? Oh, sorry, not able to hear me. We can start. Okay, now I can hear you all. Right, can we start? Okay, fine. Last Friday, no, not Friday, last Friday, Friday before, 2 Fridays before that, we were at the place where we had just started our understanding of the basics of the displacement load called earthquake ground shaking. So we will start with that as a background. So all right. My screen is visible. Okay, fine. So we will start with this, the last of the displacement loads, but one of the most significant displacement loads is the ground shaking caused by earthquakes. All right. So now, fundamentally, IRC currently expects you to design it by calculating an F earthquake, FEQ, in the transverse direction. And it has to be carried out for all bridges on the basis of the simplified rules that are described in the code, which starts with peak ground acceleration defined by the different zones of India, followed by the response of a single degree freedom time period and the inertial mass of the system, primarily treating them as a single degree of freedom system. Now, where do you think this model will fundamentally break down at the basic level? You can think of any situation where this single degree of freedom system will be the least accurate. Any idea? Anybody can suggest a situation where single degree systems, which are commonly adopted for earthquake uh, design, stops being valid. Otherwise, significantly, it is a valid assumption, reasonably accurate. Reasonably, I would say perfectly accurate, but reasonably accurate. So, where would this system actually break down? I expect this to be evident to people who have seen some arrangements in Nagpur, Jaipur, possibly now in Chennai, but not visible yet, or Bangalore. Yes, people in Bangalore should know also where this particular concept of a single degree of freedom system breaks down.
If
Why?
double decker,
Absolutely correct. Absolutely right. So wherever you are having double decker structure, this concept of a single degree of freedom is not correct at all. But therefore, one has to look for alternative methods of analysis. So FEQ, the earthquake force, is required to be calculated by the codal provision as a single degree of freedom. We are saying generally, let us say 90%, 95%, even 99% of the structure, this is not so bad, except that you don't follow the simple rules in case of bridges with very long spans more than 150 meters, wherein you have to do special investigation to arrive at the basic parameters, plus you have to do special analysis according to the code. We will try to understand why it is so. All right. So uh, essentially, the whole process of, please remember that we have classified this as a displacement load. However, we still go about designing it for forces. Because currently we'll understand this whole process of what is this force-based design and what are the alternatives to it little later. But right now, essentially what we are doing is we are transforming the forces, I mean the relative displacement between the inertial mass of the superstructure and the foundation, the relative displacement between them. It is through a structural member called the foundation, substructure, bearing, and sometimes partly superstructure itself. That whole structural member is subjected to relative displacements, and when you have relative displacement, forces will start appearing. And that force is what we have qualified ourselves, I mean, we have decided to call it as a F earthquake. All right. So our whole process today, as of date, it stands at determining this FEQ, and we do that in a simplified fashion of calculating a horizontal acceleration coefficient or horizontal acceleration value, and we multiply it with the inertial masses, which is primarily dead load, and sometimes part of the live load. Now, and the design seismic coefficient, we calculate, we are being given an expression Z by 2 into SA by G into I by R, in whichever form we want to rotate it. I mean, combine these quantities. So Z by 2 represents the peak ground acceleration, or I should say Z by 2. Z represents the peak ground acceleration. Z by 2 represents the design peak ground acceleration. I represents the importance factor for the structure. SA by G corresponds to the single degree of freedom design acceleration spectrum response value for a particular time period, a fundamental period of the structure, and R represents the response reduction factor. We'll understand the significant little later. What do all each one of these practically mean? So the first part, let's understand the zone. The zones or the seismic zonation, or the basically these values represent the peak ground acceleration values. Peak ground acceleration, zone 2 to zone 4. Earlier there used to be zone 1 to zone 5. Now zone 1 has been kind of merged and combined into zone 2. So basically now we have 4. Rest assured, there's a draft version of IRC IS 1893 out in circulation for public consultation, which is making the change further, and it is changing it from zone 2 to 5 to zone 2 to 6. So there will be a zone 6, and primarily most of the changes are occurring where the zone 5 is divided into 2 parts, and the zone 6 is going to have a peak ground acceleration of 0.76. 76% of the inertial mass will be the horizontal force in those, and that will primarily consist of most of this Himalayan belt here. Anyway, I will not talk about it now. You'll see, you can locate it in the draft of 1893 that is under circulation for public consultation. But basically, this zone represents the peak ground acceleration as a fraction of acceleration due to gravity in the horizontal direction as a single degree of mass system, assuming 5% as the damping. So then comes the question, we modify the design forces and apply these importance factor. That is based on the classification of the bridge, the normal bridges, important bridges, and critical bridges. So these are the values of I that we incorporate in this expression to derive this AH. Now question is, what are normal bridges, what are important bridges, and what are critical bridges? Some definition is seen in the code, but a fundamental philosophy is critical bridges is something that is essential, very important, and therefore cannot be lost during an earthquake event, should suffer what they call it in the design earthquake, should suffer minimal damage. And that what it means is, imagine that there is a particular region, say something like Delhi, which is currently classified under zone 4. In Delhi itself, you can have bridges which are classified normal, they can be classified as important, and they are classified as critical. All the three are possible. So they will all have the same zone factor, but the design forces each of the structures that will be designed to will be different. Normal means it can suffer significant damage. Important, it can suffer some damage. Critical means it can suffer minimal damage. Damage, nevertheless, all of them will suffer. And the whole idea is in the design criteria, there is no significant, there is no collapse. But it's the level of damage that under the design earthquake that they can suffer that is controlled by this importance factor. Now comes the concept of the horizontal spectral acceleration coefficient, SA by G. So basically, the ground displaces this way, and the superstructure, due to its inertia, is in a 180-degree phase difference. When the ground is here, the tendency is here, and eventually, if you notice, this ground acceleration will shake and it will stop. But this structure, due to its absorption of energy, will continue to go through a few cycles of oscillation in its natural mode, and it will die down after some time. And how many cycles it takes to die down depends upon the damping coefficients and the damping energy systems that are built into the structure. Significantly, SA by G has a typical graph like that, from a structure which is very stiff, in which the natural period is very small. It's a value, and from there it goes to a peak, and then it drops down. How do you determine this single degree of response of any bridge structure? You essentially do a mathematical model in which, say, this is the mass and this is the spring. Essentially, what is the spring represent? It represents, the mass is nothing but the mass of the superstructure. The spring represents the horizontal stiffness of the combined system from soil, foundation, and substructure and bearing put together. Quite often in the current stage of designs, most of the time, we ignore the soil. But if we do include the soil, it alters the picture dramatically. So excluding the soil, we do the modeling of the spring, and we come back to this value of K. And in case there is a significant damping, we introduce this as a damping model as a part. Along with the stiffness, you have a damper. And this is where we apply the acceleration spectrum, and we see what happens to the amount of force and acceleration that we see on this mass. And the acceleration spectrum is something that's a record like this, which depends upon the time. As you can see here, it's a recording of the Bhuj earthquake of the 90s. And what you see here is that between 30 and 60 seconds from the initiation of ground tremors, you had the peak acceleration, with acceleration peaking at as much as 0.98 g. This is the ground acceleration felt at the recording station, wherever it was. Okay. And a second recording of the same thing at a different location, which said it's the same 30 to 60 period, you had a 0.78 recording. So multiple earthquakes, when they happen, they have multiple records. This accelegrams are put as input to the system, and we find out the acceleration response on the mass m, and then we generate what is called as a displacement response spectrum, velocity response spectrum, and acceleration response spectrum. And all of them have a certain common characteristic, which is that all of them have a zone of concentrated peak acceleration. We naturally, normally, when we say this is how it will look like, but the design value will be shown something like this. And primarily it is because we eliminate the local peaks, because of we see in the next slide what are the things. And if you eliminate the local peak, there's always a zone of constant acceleration response. There's a zone of constant velocity response, and there is a zone of constant displacement response. Eliminating the peaks, please understand that is important. Okay. So why do we do that? We basically do that because the real spectrum will be irregular in shape, because it is more or less linked to the irregularity in the appearance of the natural ground acceleration. That is, the ground acceleration is not a regular shape. It's a constantly varying in fractions of a second. And because in all these computations that we do, the certain material properties and certain geometric properties are all approximate. So using an approximate value and calculating the precise, catching the precise peaks for design purposes is a pointless exercise, and therefore, since the natural period cannot be calculated with great accuracy, we ignore the local peaks and valleys, and hence a smooth design spectrum is used for design, and that is where finally it comes to this kind of a picture. This is a picture from IRC. Unfortunately, it does not reflect the constant displacement zone. It reflects only the constant acceleration and the constant velocity zone. Actually, there will be a small kink there. If you, I don't know whether I have reproduced that anywhere. No, I have not reproduced it. If you go have a look at the Eurocode, you will see it. So let me see if I can share quickly with you the shape of the uh, uh, of the curve as it is I defined in the Eurocode. Let me just see quickly. I think I have somewhere here on the I think this is a good slide to see this comparison. Okay, if you notice this is a side-by-side view of the time elastic acceleration response spectrum as is codified in the uh, IRC 114, wherein you have constant acceleration and thereafter you have only got a constant velocity zone. Whereas if you take a look at Eurocode, Eurocode has constant acceleration. Then from here to here you have the constant velocity spectrum, and from here to here you have a constant displacement spectrum. Please remember one thing, that if you get given any one of them, if you are given the constant acceleration, this elastic acceleration spectrum, you can get the velocity spectrum also, velocity response also, displacement also, all can be calculated from each other. So that should not be what they call it a worrisome project. In the sense, if you take a look at this, this is the constant acceleration when you convert it into displacement response, and this is the constant velocity, and this is the constant displacement. Basically, it's nothing but if you do the integration of this curve, if you notice this is which is time constant. So if you do the second integration, if you integrate acceleration twice with respect to time, you will get displacement. And this is the constant velocity. If you recall your definition, it is proportional to 1 by t. So if you integrate it once, you will get the velocity spectrum. So you integrate 1 by t once, you will get a constant value. So this becomes the spectrum of constant velocity. And this curve, if you take a look at Eurocode, is proportional to 1 by t square. So if you take the second integral of acceleration, you will get displacements. So this will become the zone of constant displacement. So it is possible to derive. We have decided in India, we are not yet interested in the acceleration and velocity and displacement yet, because we have not yet formulated our design specification for that yet, but we will get there. Now that we have a new zone map definition, all the magnification has taken place, you will find that design is going to be more difficult with the new code in place. IRC will also have to change with that. So IRC will undergo a lot of changes once that new 1893 is published. Okay, so I'm just introducing to what are the changes that are likely to come. So this is, you can see the pattern itself will change. So with that, you will also have what do you call it, a different kind of design approach that may have to be learned and adopted. So coming back to our understanding, basic understanding of the seismic displacement loading. So we need this parameter, and for which we have this fundamental. And if you notice one thing, our irrespective of the soil type, we have the peak acceleration is constant. If you recall the Eurocode, even the peak is different for different soil types. Okay. Then, and as I told you, if you look at the graph for the constant acceleration zone, SA by G is constant 2.5, 2.5 for all soil types. And after that, the acceleration spectrum is proportional to 1 by T. So if you integrate acceleration, what do you get? You get velocity. So if you integrate the second part of the curve, what you will get will be a constant velocity spectrum. And if you do the second integration, you will get a linear one with respect to time. So displacement spectrum will be linear in this zone. So according to current IRC, displacement spectrum goes on increasing to infinity, which is not really the case. All the systems that we have studied and analyzed and taken, they all demonstrate reaching the constant. So this graph also will get changed. This definition will also change, and we will have a definition of constant displacement. And the constant displacement is actually defined in our code indirectly in IRC SP 114. I'll not talk about it since we are not dealing with learning in depth about the earthquake design. We will look at understand the phenomena and be aware that these are the issues that you must be aware of in time to come. Now, so after you have the fundamental natural period, that is the first period of the bridge, you can use any of the rational method, or for small bridges, you use the simple equivalent static method, which is suitable for small displacements, stiff bridges, etc. And you calculate the modulus of elasticity as per concrete. You use the cross section property, and we use the computer based modal analysis, mass and stiffness modeling. You can do, these are all the various rational methods of analysis that we are allowed to do according to the code to arrive at the FEQ, right? So after you have that, and there's also given a simplified equivalent static method, which is nothing but time is equal to time period. First mode of is 2 into square root of d by 1000 f, where d is the appropriate dead load and in kilonewtons, and f is the force per unit displacement. That is the force required to produce 1 mm of horizontal displacement. So if you do any static methodology to calculate this, you have a simple way of calculating this time period. And so you can actually derive it from the fundamentals of structural dynamics. It's very simple. Maybe sometime else, or maybe later in the slide, I may have shown you how this is arrived at. But remember, this is a simple method for primarily useful for whenever you're using the equivalent static method. It is not suitable for any modal method or any more complex ways of analyzing the FEQ. Now, when the ground shaking happens, if you take a look at it, a system in this direction, wherein this mass, center of mass is indicated, and the shaking takes place in this direction, then what you will see will be a displacement, that if the two piers are of nearly equal stiffness, then you will find that the displacement, both the piers are undergoing similar displacement, and therefore you will practically see no force system on the superstructure. However, if the two substructures are of unequal stiffnesses, in that case, there will be a relative displacement between the two ends, and depending upon your bearing articulation and the load carrying mechanism, it might induce a certain amount of force systems in the superstructure also. Otherwise, primarily the substructure and foundation will be subjected to lateral forces. The same thing if you take a look at in the longitudinal direction, say you have a pinned and the roller one. When you do that, what happens is the displacement takes place in one direction, the mass moves, and all the forces appear on the so-called fixed end, and the free end will see some force primarily due to the friction at one limit, or alternatively due to the distributed mass of the substructure itself, it will see some amount of seismic response as a distributed mass. But essentially the lumped mass of the superstructure will have its inertia connected to one pier, where, as you can see here, is the pinned support. Okay. Now, the fundamental period for equivalent static, you go back to structural dynamics, it's simple, square root of k by m, right? And time period will be derived from that as 2 pi into square root of m by k, if this is the frequency. And then mass you substitute by, if you took it in terms of weight by g. That's why you notice that the d has to be put in kilonewtons and not in terms of kilograms. it has, or tons, it has to be put in kilonewtons so that you convert it into force, and we are divided by G. Therefore, this and this 1000 F, it comes from that kg to kilogram. That kilo is converted into this, right? And this 2 pi, if you take a look at this 2 pi term divided by square root of G, a pi will be, pi divided by square root of G will be approximately 1. If you recall, G is 9.807, you take the square root of that, it will be about 3.1 or so. Pi is also 3.1. They cancel out, so therefore it simplifies into 2 into square root of D by 1000 F. Here the units are important. Don't forget the units. The time period is always in seconds, but the D has to be self-weight, not mass, because we have incorporated the acceleration due to gravity into it, and that has come out and cancelled out this pi. Okay, and the force, and this force also, since this is in force unit, this is also force per unit displacement. So it has to be applied in the magnitude in terms of kilonewton per millimeter, not ton per millimeter, not kg per millimeter, but kilonewton per millimeter. Okay, so that's how you have to determine. Basically, you can do any software, you apply a force that is required. So you known force you apply, evaluate the displacement, and therefore you calculate force per unit displacement, or any other mechanism is good enough for you to determine the F, and mass is known to you. So this procedure is a simple way of calculating the equivalent for the equivalent static method. Okay, but after having determined the FEQ, we have different components, and the different components are designed for different values of forces. So what are the forces? What are the structures we need to design? We need to design substructure, foundation. We need to design substructure. We need to design bearing, and we need to design superstructure. So now the question comes, the response reduction factor that you see in the code is primarily to tell you where do you want to accommodate your, remember, what is the problem statement for us? Problem statement is how to accommodate the relative displacement between the ground and the superstructure. So what are the components that will can accommodate, which are the components that can accommodate this relative displacement? Which are the components? Superstructure is quite rigid. Foundation. So now comes the question, which one of them should accommodate the maximum relative deformation? Why not bearing? Why not foundation? You have chosen substructure. I want to know why not the other two? If it is rigid, will it accommodate the relative deformation? Yes, please. Others. We have to accommodate problems. Please remember, let us recap. What kind of loading is seismic? Displacement. Displacement. What displacement between what and what? Okay, so you have identified the components that lie between soil and structure are the foundation, the substructure, and the bearing. Out of which one should accommodate the maximum displacement? Yes, please. And now you changed. You were for
What is the
substructure
type
some
of
kind.
bearing, sir?
Huh?
Which type of, what is the type of bearing
That
we
is
use?
your choice. You are the designer. You are the designer. See, when we are learning engineering, we are not, we know this bearing will cater for these effects. So we know the choice. The question that I ask is, your problem is the relative displacement between the soil and the superstructure has to be accommodated. The question is, which component should accommodate the maximum relative deformation? Bearing. Okay, fine. So Kalyan has changed the party. Substructure party has moved to bearing party. Saudharni was sure. How many of you agree with
Okay,
that?
plus 128 plus 128 plus 136.
Whatever is having a low stiffness will accommodate good displacement.
528 or
You are telling
628?
what will have. I am saying
What will have.
what should have. You remember
Okay.
one thing.
136.
You are the designer. You choose. You choose what you want it to do.
Okay,
It is your decision. So Sukalyan goes for bearing. What about others? No opinion, or have opinion but keep it to myself? Then I have to take a poll. Others can quickly voice out their view. What do you think is the best place to accommodate the maximum relative displacement?
Bearing.
बाकी portals में क्या होगा?
Okay,
Question
Bhavdharni
number
also says bearing. What about others? Quick poll. Start with Nadeem, Akhtar. Yes, please, quickly. What happened? Somebody vanished. Okay. What about Praful? What do you think? The component that's best suited for accommodating largest relative displacement. No opinion. What about Saurabh? No opinion. Shujit?
So I think bearing was.
Okay. Shujit?
I think so too, sir. Bearing.
Bearing. Okay. What about Milind?
मेरे को भी लग रहा है सर बेरिंग.
Okay. What about Shreya?
Sir, I also think it's the bearings.
Okay. Nayana?
Bearing, sir.
Bearing. Okay. Bhavdharni has pegged her. She's sitting on the fence. Last time I heard. So has she made up her mind?
The bearings only.
चलो मैं उसका मेल रिकॉर्ड में
Bearings.
चेक करके
Okay.
आपको.
So all of you are strongly going in favor of bearings. Now, if I have cotton PTFE bearing, will it accommodate relative displacement relevant to the earthquake? Say we are talking about transverse earthquake. So obviously on one pier we need to have one guide, at least one guided bearing, if not a pin bearing. So for ease of understanding, let us say that the so-called hinged end has one pin bearing, and the so-called roller end has a longitudinally guided bearing. So in that case, will the bearing accommodate relative displacement in the transfer when the ground movement is in the transverse direction? Will it accommodate? Now we'll start with Sukalyan again. What about others? Praful and Akhtar had no opinion, so we'll call the others now. Saurabh, Shuvdeep, Milind, Shreya, Nayana, Saudharni. Can you quickly? Let's move on faster. Where do you think will it happen? will it happen? Will the relative moment be accommodated in the bearings if we choose to do pot cum PTFE bearing in the fixed and the free end, obviously. So question is, in the transverse direction earthquake, will we have relative displacement between the superstructure and the substructure at the bearing in the when the displacement loading is in the transverse direction? Will it happen? What happened? Complicated question. Let's
No,
take a
sir.
look at. So let's take a look at the picture again. So we said that for the important PTFE bearing, between these two bearings, at least one of them is locked from relative displacement between superstructure and shear cap. So there will be no relative displacement. So that means for accommodating that displacement, this bearing is ruled out. What does that leave you? It leaves you substructure and foundation. Correct? Now, concrete as a material is a fairly stiff material. So it can accommodate some amount of displacement, no doubt about it. After all, moment and curvature have a relationship for concrete. So I want to accommodate more displacement. So how do we do it?
By ductile detailing,
Where?
That is somewhat.
plastic
Where will the plastic zone be in that case?
bottom
Okay.
of pier.
At the bottom of the substructure. Can we have plastic hinge forming in the foundation?
No, sir. It is not recommended because it is within the soil mass.
It is not easy to repair post earthquake. It is not possible to repair post earthquake, whereas if the plastic hinges are formed in the maintainable zone. So therefore, you are saying relative displacement is possible to be accommodated in substructure. Now I'll come back and ask you, no, I don't have potent PTFE bearing. I have elastomeric bearing. Then what happens?
The displacement taken care by elastomeric bearing itself, no ductile detailing is needed or not?
That is no need. Now the question comes, so therefore, this response reduction factor R, it depends upon the element that is accommodating large relative displacement. That is, you are allowing certain amount of non-linear deformation to take place. Now, the question is, if you are taking, and remember one thing, once the relative displacement is accommodated, and you have allowed for large deformation to take place in one of these components, either at the base of the pier, in case the bearing type is potent PTFE, or where the relative displacement in superstructure and substructure is arrested by any mechanism whatsoever. Then the next place you have is formation and creation of plastic hinges, so that there can be significant relative displacement between the superstructure, thereby accommodating this displacement loading. Now comes a question, displacement is known, but the stiffness is reduced by allowing formation of plastic hinges. So what is the force you design it for? Large or small? Listen to the question carefully again. The relative displacement between the superstructure and the ground is known, because that depends upon the intensity of the earthquake and the inertial mass of the superstructure. The relative displacement is known. And that displacement is getting translated into force. What is the parameter that comes into picture? What is the parameter that translates displacement into force?
Stiffness.
Stiffness. So now the question is, if I allow formation of plastic hinge here, what am I doing? I'm enhancing the stiffness or reducing the stiffness? Reducing the stiffness. So if I reduce the stiffness, while the displacement is same, what should be the force I will get? Larger, smaller.
Smaller force only.
Smaller force you will get. And that smaller force is how you get it by defining a response reduction factor greater than 1. So what do? We say that this junction will be designed for a force smaller than FEQ. It can be a factor 2, 3, 1/3, 1/2, 1/2, 1/3, 1/4, 1/5, 1/9, depending upon the type and structure and the nature of the material. So we designed this for a smaller force. And then what do? Then there are other design rules to make sure that you don't have a mechanism developed elsewhere, and therefore you have for a single degree of freedom system. Because remember, we are still understanding this phenomena as a concept based on single degree of freedom. That means there's only one mass, there's only one spring. Don't bring in other complications. So once you have this, you cannot have plastic hinge formation in more than one location. So we take other precautions, whereby we say we design the foundation for no reduction in earthquake. So we have R equal to 1. Or we say the pier is designed for R equal to 3. Some codes say you design foundation for R equal to 2. Then at the same time, in the case of pot and PTFE bearing, we don't want the bearings to fail. So we say the bearings should be designed for R equal to 1. When you say pier designed for R equal to 3 and the bearing designed for R equal to 1, what exactly are you saying? You're basically saying that I will design it and build margins of safety in all the other components so that plastic hinge forms only in one location. There are different ways of doing it. We will study that when we talk about different methods of designing for earthquake. But right now you understand that R value variation basically represents our desire and wish to control the point at which significant deformation is allowed to take place. And in case it is substructure, then R can be, in bridge code, it is currently 3. But if bearing is the one which is accommodating, then for this junction design, R is still equal to 1. And the bearings deformation, since it's an inherent property, then you will take care of, you get the advantage primarily in the fact that the flexibility is reduced, or rather it will increase, and therefore your time period is large. And if the time period is large, from the response spectrum, you realize that you get a smaller design force by itself. Whereas in this case, we don't alter the time period, we alter the design force to a desired level. So that is where there is a response reduction of component by component. You will have a different response reduction. And if you take a look at IRC code, you have all these various response reduction factors that are depending upon the nature of the material or the type of the structural arrangement. And if you notice, for all bearings and connection, it is always 1. Okay, please understand one thing. This applies, bearing and connection applies all, irrespective of whether you have a plastic hinge formation in pier or whether you are using a isolation bearing type which accommodates deformation by itself. Either way, the response reduction factor is 1. Now, in the bridge design, we design for earthquake all bridges in zone 4 and 5. But in 4, we leave out culverts and minor bridges up to 10 meters. We don't design them for earthquake. This is one way of telling that don't put the onerous conditions of the earthquake design on such small structures, which can see significant damage. But in zone 3 and 2, the exemption category is different. For culverts and minors, they're definitely there, but for spans less than 15 meters and total bridge than 60 meters in zone 3 and 2 also, you don't need to do seismic design. So you do it for longer spans only, because of the essentially from the point of view of the fact that these structures will be so many in numbers that if you start putting this onerous condition, things might become expensive and difficult. So that's a cost benefit trade-off. Okay. Now we have seen this so far as the ground shaking in the horizontal direction. However, earthquake accelerations are in all the three directions, X, Y, and Z. All right. But when it comes to Z direction, what happens is this acceleration is transmitted through the substructure. Superstructure has a distributed load, has its own inertia, and we have been given a simple formulation which says that the design seismic vertical coefficient, you take it as 2/3 of the design horizontal seismic coefficient. But remember one thing, when you do this, the time period that you take will be that due to the vertical stiffness of the deck and not the lateral stiffness. Don't confuse that. Your time period you will take will be that, and time period will be that of a beam bending in the direction and not a free cantilever as in the case of a pier. So you have to be very careful about what you understand. So with that natural period and the response spectrum that you have got, you calculate the value and take 2/3 of it for the seismic vertical coefficient and combine it with forces in the other direction for simultaneous occurrence of the multi-directional earthquake. Okay. Now we have been seeing this all from the force point of view. Quite often, if you take a look at this example, wherein you had a slab resting on it, we find that while the force were all okay, substructure didn't see anything, but the displacement aspect was completely ignored. And what has happened is this span has got dislodged and has fallen down. So that is why you have to understand one thing, this seismic design has got two parts. One part is the primarily displacement part, but for design strength purposes, we convert it into an equivalent force and we design it for it. However, we cannot ignore the displacement part, which is the primary component, and it is catered for currently. Currently, if you understand, all our codes are written on the force-based design. So the displacement aspect of it is addressed differently. It is not that we have ignored it in our codes, but the displacement aspects of it is considered in the following fashion. And another example of it is this bridge is actually a submersible bridge that they have built across Narmada. And for preventing during the submergence time, there's a possibility that this bridge can be washed away due to the water current. Why? Because the water current is highest, farthest from the depth. That means the water current at the superstructure level will be very high. And therefore, to prevent its dislodgement, they have incorporated these stoppers. This device actually helped this bridge survive the Bhuj earthquake because it prevented the lateral displacement. So there is one way to arrest the displacement is to provide for anti-dislodgement device. One way, that's not the only way. Okay. What does the code do? The code does it prevents dislodgement. It has a seating width requirement. This seating width requirement in our code has been reproduced from AASHTO. It has a basis, the background of it is reproduced from AASHTO. Basically, if you take a look at it, this is a articulation half joint. You may not see much of it, but still, some people still, in certain circumstances, use this half joint. So you have one superstructure and you have another support or extended pier, and you have two different spans. They are sitting on each other. What should be the overlapping length n? And that is given here. It is described as a constant value plus 2 times the length and 10 times the height of the column in millimeter. This is an empirical relationship. So this is how another way to prevent dislodgement is. This is also built into our code. If you take a look at in a slightly different fashion, it might be there. It may not be exactly this formula. This has undergone a multiple change. This was when it was in IRC 6, but if you take a look at IRC SP 114, which is now the new earthquake code, you will find a slightly modified version of this class, but nevertheless something similar to this. It tells you what should be the seating width dimension. The aim of this is to prevent to cater for the displacement design empirically, not with hard science behind it, but empirically prevent it, and we prevent dislodgement by providing for this seating width requirement. Now, what does it mean? This requires us basically to generate, dimension the pier cap generously. Don't be stingy with it. That is what is the basic guidelines for this particular aspect of the design, that you need to provide the articulation more generously. So how do you do it? If you have this articulation, you don't change the bearing size, you just make sure that the overlap, seating overlap between one structure and the other structure is magnified. And in the case of this abutment, similarly you magnify it. And in the case of pier, again magnify. This solution is also a solution that is acceptable in terms of preventive displacement. Now the question comes, if you notice, if you have ever read different codes, AASHTO doesn't have any prescription for anti-dislodgement arrangement. It doesn't have. It, however, has this prescription for the minimum seating width. What does our code do? Our code not only reproduces this seating width, in zone 4 and 5, it also wants an anti-dislodgement device somewhat similar to this. So our code has, maybe it is the case of once bitten, multiple times shy. So they have seen earthquakes in which nothing has happened to substructure, nothing has happened to superstructure, except that the superstructure is lying on the ground. So therefore, they said dislodgement is a bigger phenomena in high seismic zones, so it has to be catered for more seriously by seismic arrangement. So we have 2-3 things to satisfy in our code. We have to satisfy the force strength base, because we are all strength based design. We have to satisfy the seating width requirement, which is essentially to prevent displacement based failure. In addition to that, in zone 4 and 5, we have to have an additional stopper arrangement in both the longitudinal and the transverse direction. So how do we do that? So we have what is called as a seismic reaction block. Okay, so imagine in a longitudinal direction you have a multi-span continuous structure. It need not be structurally continuous, but for longitudinal displacement, imagine that it is continuously. And in transverse direction, there will be restraint in every pier. Okay, so this is the normal operational condition. Now, what backup measures do we need? We need to make sure that we have an anti-dislodgement device. How do we achieve it? On the fixed pier, you introduce these purple-like stoppers, which essentially prevent the longitudinal displacement. And in transverse direction, you introduce this dark blue kind of arrangement in the fixed pier. So that prevents the transverse displacement, in spite of the fact that your bearing articulation might already be preventing that, So in zone 4 and 5, you need to make this additional provision. And if you take a look at the other piers, the so-called the free piers, they don't have the longitudinal stoppers. They only have the transverse stoppers, in addition to whatever provisions you have made in the bearing. In which case, in the case of zone 4 and 5, in zone 1, 2, and 3, you may, or I don't know, I don't remember exactly, maybe zone 3 also requires you to provide this additional. I don't recall, but you can refer to IRC 114, SP 114, it will tell you that zone 4 or 3 also requires you to have this additional stopper. Okay, so this is how we take care of, see, our basic phenomena is displacement, but we design for force. But the displacement phenomena we have not ignored. We have not given any design rules for how to handle the displacement in our code, but we have given detailing rules how to prevent the adverse effect of significant displacement in the form of seating dimension and in the form of provision of seismic restrainer blocks. Okay, so seismic reaction blocks, they are detailed out in very much in the transverse direction. As you can see, there's simply a corbel-like projection around the superstructure, so that any lateral displacement is within a controlled amount, and beyond which the stopper will engage. That is the typical arrangement in the transverse direction. So with this, we are through with basic understanding of seismic effects as loads. And next, we will start understanding the concept of the characteristic loads and the way in which it differs for different types of loads in the coming Friday. So now I'm open to some question on what you have heard in the last three lectures. Okay. As I said, I'm open to questions from the last few classes or anything else that has been bugging you, with which you think you can discuss in this forum. No problem. Yeah. Okay. The reason for it is generally in a typical bridge design, bearings don't have redundancies. If you take a look at the what we call it, the concept that are generally followed in the advanced design standards. If you notice, in our case, in our country, what have we done? We have built in different forms of redundancy. Just now we looked at, now in the case of blast loading, what is our biggest problem? Our problem is the loading is of a very large magnitude, and to cater for that loading significantly, we have to use non-linear characteristics of the material to be able to generate enough capacity to resist the load. Unfortunately, most of the bearings that we design are all meant to be designed and used in the elastic range. They do not have, we don't allow them to be used in the plastic range, so we don't build in that kind of capacity. Second, the bearings don't have redundancies. What I mean to say is that if, for example, the blast subjects the superstructure to significant lateral load, the question is, we have not catered, let's say the blast is happening in zone 2 or 3. We have only got the bearing to transfer all the lateral loads, and that bearing can easily be overcome by the blast load. But if we take in zone 4 and 5, at least some amount of redundancies which we have built in, primarily not for catering for blast load, but for catering for the seismic forces. In zone 4 and 5, we have an additional stopper arrangement. So that will take care to some extent the dislodgement of the superstructure. So in the case of blast loading, bearing is considered the most vulnerable because it doesn't have any redundancy. You cannot build in non-linearity, behavior, plasticity, etc. We cannot build into it, and nor does it have redundancy, only except in the case of zone 4 and 5, but that is incidental rather than through design for other reasons. But for all the other zones, we have very little margins to take care for excessive forces that will appear due to blast. That's the reason why I say the bearings are the most vulnerable parts in the case of zones which are susceptible to blast loading. But remember one thing, blast loading is something that has to be catered for only in the area where you anticipate risks of that. Normally what happens, it is throughout the world, very rarely does anybody cater for bridges with blast loading. They cater for reactor buildings for blast loading. They cater for a critical power structure for blast loading. They cater for critical dams for blast loading, but they don't cater bridges for blast loading because the amount of damage in terms of people loss that can happen by dismantling of a loss of a bridge by a blast is very minimal. So normally it is not designed. So you will not find too many examples of bridges, but critical buildings. Suppose a building is storing very important data as far as the nation is concerned, then they may design the building for blast loading. But then they will also minimize the risk by making such buildings have a security arrangement which prevents the blast from happening very close to the structure. Please remember one thing, if you recall the pattern of the blast loading, the moment you decrease the distance of the blast from 20 meters to 10 meters, the blast pressure goes up like hell. And from 10 meters, if you reduce to 5 meters, you can virtually not design it. So what it means is, if you think there is a vulnerability, you make sure that you reduce the vulnerability as much as is possible. But as far as the bridges is concerned, the reason they rarely are the bridges designed for blast loading. And even if we do the blast loading design, we generally tend to, wherever we perceive this risk, very rarely do we do bridges with bearings. We try to make sure that the structures are integral, because then in the concrete or the steel material we can build in the necessary plasticity and large deformation capabilities. So if you have no further questions for the day, we will call it a day today. We'll meet again next Friday. Now we'll start from, now we have got a gist of all the various loading. Now we will start understanding the concept of characteristic loading in the next class. And after that, we'll move on to analysis, different methods of design and things like that. Okay. If you have questions, we'll give 5 minutes chance to anybody to ask, or we'll call it a day. You decide and let me know. Okay, then we'll call it a day. We'll meet next on 17th. All right. Okay, right. See you then. Good night. Happy New Year to all of you.
Happy New Year, sir.
Happy New Year, sir.
तो यहाँ पे हम लोग